Once again, welcome to my YouTube channel, Pearson and Excel International Maths by Mr. Kamotho. And we continue to understand integration in pure mathematics 3, this book, and of course we are discussing example 3. And in this video, I want us to look at example 3, part B, which says that integrate e raised to power 4x plus 1 with respect to x. And as we know, or as we have said before, anytime we are integrating a function, we should consider that we are going back to the function. Anytime we are integrating, we must consider that we are integrating a gradient that takes us back to the function, simply because if we had a function which was y, again, if we undertake differentiation, then we should get to the gradient. If we have a gradient and we integrate, if we integrate a gradient, then we are going back to the function. So this is, we are integrating, and now we are going back to the function y. What does this mean? We know very well, since the integral of e raised to power x is equals to the same e raised to power x, and we know it. So we know it is very possible that the integral of e raised to power 4x plus 1 may be equals to the same function e raised to power 4x plus 1. So if we consider this to be y, let y be, so let y be e raised to power 4x plus e raised to power 4x plus 1, such that now the dy dx is going to be e raised to power 4x plus 1 multiplied by 4, having applied the chain rule. This is 4x plus 1, having applied the chain rule there. And this is 4 e raised to power 4x plus 1. I want us to compare that with what we were to integrate. We have differentiated what we suspected would have been our function to give us this gradient, and having done that, it has given us 4 times of what we wanted to get. That means whatever we differentiated, we ought to have differentiated a quarter of what we differentiated, and therefore y should have been a quarter of e raised to power 4x plus 1. Why do we say this? Such that now the dy dx of this is going to be e raised to power, or rather a quarter, e raised to power 4x plus 1, applying the chain rule, times 4. Now this 4 and this 4 cancel out, and it gives us e raised to power 4x plus 1, and that is it. So our y should have been this. Therefore the integral of e raised to power 4x plus 1 is exactly equals to a quarter e raised to power 4x plus 1 plus, of course, a constant. And that is the end of the story as far as example 3 part B is concerned. And in the same kind of video, I would want to explain example 3 part C. And in this part, we are expected to integrate sec squared 3x with respect to x. Again, we should look at sec squared as a derivative of something. Yet we know the derivative of tan is sec squared x. And of course, if the derivative of tan is sec squared x, that means therefore when we integrate the derivative, we should be getting back to the function, and therefore try our y to be equals to the tangent of 3x, because we know when y is tangent 3x, our dy dx should be sec squared 3x, that we know. And when y is equals to the tangent of 3x, dy dx is going to be the sec squared 3x times a 3. Why? Because of the chain rule. We have to differentiate the whole expression multiplied by the differential of the inner part that is containing x, that is chain. The application of the chain rule. This gives us 9. This gives us 3 rather, not 9. 3 sec squared 3x. Look, it has given us 3 times of what we needed. Therefore, our y should have been a third of this. And this makes us believe that the integral of sec squared 3x with respect to x is going to be a third tan 3x, of course, plus a constant c. And that is just like it. Please repeat these videos and watch them several times. You will understand. That is the end of example 3. And of course, we expected to be very keen as far as this part of this topic is concerned. So again, visit my YouTube channel, subscribe, and share widely so that we can work together. Okay?